Hello, everybody. Welcome to the bioseparation lecture. This talk we will focus on the differential extraction. I talked to you already about the continuous extraction or stack extraction, and batch extraction. Now we will consider the differential extraction. Mostly the differential extraction apply in like the chemical industry, mostly used, and also is a like low application in the bioprocessing. Right. The differential attraction is occur when a heavy liquid phase and a light phase, that's light heavy liquid and light liquid phase continually flow past one another. That's like open. So you will transfer from one phase to other phase, but it is never fast enough to reach the equilibrium. To reach the equilibrium. I will show you right this picture, an example of the differential extraction. Like for this, we can see that like we feed like this is feed of light liquid and feed of heavy liquid at the top for downward in the bottom, and light liquid feed at the bottom and for upward and now at the top phase. In this phase, we have like the packing with me. For that case, that's like the light phase and heavy phase contact. That's like contact each other in the packing with made, and also we have the mixing like this impeller to mix it. Right? Impeller will disperse the heavy phase and liquid phase mix together is better, and also will pass for like the maze. Like this made packing will help to the liquid phase and light phase contact better. Contact better if these two phase contact. It also will induce the mass transfer between liquid phase and light phase. Light phase and heavy phase. Mostly the solute from heavy phase will transfer to the light phase. If we have like small contact area like this, it's improved the mass transfer. This is the first one example. With the first example, this is the counter current flow in different direction. And the second one is also like the counter current for the light liquid phase flow in at the bottom and out at the top. Heavy liquid phase flow in at the top and out at the bottom phase is called counter current flow. That's counter current flow. But there is no the packing for this. There is no the packing. But they have like some plate like this. We have the plate, and also we have the mixer like this. This is mixer between liquid phase and gas phase can contact each other and then mass transfer. And another one, this is also, it look like this, but we have like a lot of the rotating this or impeller. Right? We increase more rotating impeller. And this data link, is it a fixed, is move, right? And also this light liquid phase for upward, heavy liquid phase for downward for this case. And there are also another technique. For this case, we call like this spray column. Spray column. For this one, the spray is liquid, light liquid phase is spray at the bottom. And heavy phase for downward, spray for downward. It is contact with the light liquid phase is dispersed because we spray dispersed in the bottom. Dispersed light liquid phase upward, heavy liquid phase downward, and mix together. We contact together mass transfer. So you will transfer from heavy phase to the light phase. And another one, this is it's opposite. The heavy phase is spray, right? Dispersed phase downward, and light phase is upward. That's right. But for this case, it's spray in light liquid. This spray in heavy liquid. That's right. There are also another configuration like they call this bell, right? This is another, it's the same, sorry. It should be the same, like the same, this, okay, it's the same. This is the same. This, a modify of this is increase like some buffer, like some more buffer. Okay. This is another design. Another design is the mixing, and we have a buffer, and we have the compartment buffer like this. and also it say Y. This is the rotating this contactor. This is the rotate. This is the fix some like buffer. For this configuration, we decide to improve the contact between light phase and heavy phase. If the contact more, it maybe improve the mass transfer. For the attraction, the main objective we would like to transfer the solute in the heavy phase to the light phase. If we have an area is high area to contact, we improve the mass transfer. That also it is depend on the mixing. It depends on the perfect area. It depends on the height of the column. Also, if we improve the attraction, attraction. This is like the rotating this, but for this case is symmetry. It's symmetry, but it's asymmetry. That's like the inside area. That's like the sector of this inside area. Okay. Another one like this is another design. Another design. The flow configuration. This we have like rotating this. Okay, we have like the mixer. This is another design. For this case, it will rotating bucket. We rotate some liquid contact like this. This another is a vibration. That's it. We use like the vibration, and also we have like this vibration, and also like the shaft to rotate. The shaft to rotate the buffer. It's another design for the attraction. Okay, we forgot the next we will consider like the design equation. The design equation for this case we need three equations. And the true equation is the same of previously. So this is with the state attraction, equilibrium equation, and mass balance equation. So if we consider this figure, this is the column. This is the column with along with L. The length of the column is L. We start from this 0 and L. The heavy phase flow downwards, light phase flow upward. Y0 is the solute in the heavy phase at length 0. YL is heavy phase at length L, or feed is output. X equal to 0. Mostly we feed light phase with pure. So when there is no solute, we call X equal to 0 for that case. Out as XL, as X0. Like this. This is the model of the attraction. And also for this case, we balance around a small volume. That's right. We create a small volume along the length of the column. We would like to know what happened in this a small volume. That's right. We call it the volume A dataset. Dataset is the increment in the length. A is the cross-sectional area of the column. We would like to know like this. Okay. The first equation we need is the equilibrium relationship. That's right. X is the fraction or solute concentration in the light phase equal to the equilibrium constant multiplied by Y. Y is the concentration in the heavy phase. This X and Y is equilibrium with K value. Another one is we balance. That's right. We balance allow input output. That's right. Input. That's right. For this case, there is no generation, no consumption because there is no reaction. That's right. Input minus output equal to 0 because there is no accumulation because it's flow in, flow out continuously. That means the general equation for mass balance input minus output at generation minus consumption equal to accumulation. That's right. No generation, no consumption, no accumulation. That means input minus output equal to 0 or input equal to output. That's right. If we make a balance of solute around this, what input S is amount of heavy phase or flow rate of heavy phase multiplied by the concentration is mole or mass per volume. If S is volume, that you get right amount of solute in SYL plus L X0 is the solute in the light phase equal to output L XL plus SY0. You get like this equation. That's right. because in the light feed there is no solute. Okay, x equal to 0. You get the relationship between x and y like this. X equal to heavy fat, folate in heavy fat or not in heavy fat, divided by light fat, multiplied by y minus y0. Y is, for this case, y we call this L. XL or YL is XL equal to Y. XL is X, YL is L, is Y, like this. Get this. The concentration at Y0 means concentration at Z0. Like this. And another equation that we need for this case, we will balance. So use balance in the liquid heavy phase around the column, small volume like this. Small volume like this. What happened? There are some heavy phase input at Z, at data set, output at Z, light phase input at Z, out at Z, data set, something like this. This is we only, right? But for this case, we only consider the heavy phase. Yes. Okay. We can't write the steady state mass balance. So you, for this case, we talk about the steady state. So you accumulation, there is no, 0. How about solid flow in minus out? Input minus output. For this case, input minus output. This is the, for this case, S multiplied by Y. Y is amount of solute. Input we multiply by minus 1 Y. Because for this case, the direction of Z is in this case, but S is input in opposite direction. Z input at this direction. Okay, we multiply by minus. Okay, it's multiplied by minus. For this case, is S in at Z plus delta Z out at Z is opposite, is minus. Like this. Here we get this minus S at Y at Z minus Y at Z plus delta Z. Like this. Okay, it is at Z, Z plus delta Z. But for this is opposite, we go minus. Okay. And also another one is solute minus the amount of solute transfer out of the S. For this case is equal to R multiplied by volume of the cell. Volume is, this is cross sectional area multiplied by the increment is delta set. Right. Okay. And next one we divide this by a delta set, let delta set approach 0. For this case, we consider like the definition of limitation. And then you get 0 equal to S over A divided by this minus R. In this case, we have to know what is equation of R. Most case, we talk about the rate of mass transfer, right? Of mass transfer or between solute and solvent. Solute from heavy phase to the solvent of the light phase. That we can express this in terms of the mass transfer coefficient. R can express in R equal to Ka y minus y star. K is mass transfer coefficient. That's a convective mass transfer coefficient. A is the surface area per unit volume. Y star is the concentration in the heavy liquid phase with equilibrium with the light liquid phase X. That's light liquid phase X. Okay, for this case, we substitute into this equation and then we reorganize and then we get the equation like dy by dz equal to Ka divided by Sa y minus y star. And also we substitute equation equilibrium equation, this equation into this equation, and then we get like an integration. That's why we calculate the length of the differential sector from the equilibrium line, operating line, and on heavy liquid like this. That's why we integrate the concentration from y at 0 to y at L, at 0 at to L. That's why we integrate like this. We solve this equation. We solve the equation. That's why we substitute y like this. We substitute x. Okay, we substitute y because y is a function of x like this. That's right. Okay, finally we get like the equation L is from 0 to Z, 0 to and then S over A divided by K is constant is out of the equation, and then we get Y0 to YL. That's Y0 to YL dy by Y minus like this. And finally we get like this equation. This is the length or the height of the column. Height of the literally extraction column equal to this term multiplied by this term. E is the attraction factor, we know already. That's right. We call this STU multiplied by NTU. STU, we call this height of transfer unit. The unit is the length. That's right. Number of transfer unit. Height of transfer unit, mostly we use to determine the efficiency of the attraction. That's right. For NTU, we use to measure like the difficulty of the separation. That's right. Difficulty of the separation. That's right. Higher transfer of unit is make efficiency is higher for attraction. Okay, for example, for this case, we would like to isolate or separate steroid like sitosterol from an aqueous vegetable extract. To do this, we pump 6.5 liters per hour of extract upward to a packet column with height 0.61 meters and diameter of 10 centimeters for this case. For this case, we flow the heavy phase. The heavy phase is the vegetable extract. That's like vegetable extract for upward. That's like the heavy phase is for upward for this case with the flow rate of 6.5 liters per hour. And the column height is 0.61 meter and diameter column is 10 centimeters. That's right. And also for this case, we use methylene chloride at light phase to separate the sitosterol. That's right, to separate the sitosterol from the vegetable extract. That's right, vegetable extract. Okay, we flow this downward with 3 liters per hour. That's right, downward. And we find the experiment, the K value is 11.2. And for this case, the achievement is 53% recovery. 53% recovery means amount of feed sitosterol in the liquid phase, it separate out 53%. That's right. 53% is separate out and 47% it remain in the heavy phase. That's right. Okay, the question, what is the value of Ka? K is mass transfer coefficient. A is the surface area divided by volume. That's right. And how long should we make the tower for 90% recovery? If we would like to achieve 90% recovery, what is the height of the column? That's right. But from problem statement, we know is 53% recovery. We know it the height is 0.61 meter. My question is, what is the height of the column if we would like to increase the percent recovery? And I talked to you previously. The length is equal to height of transfer unit multiplied by number of unit. If higher of transfer unit is higher length, it will increase the separation efficiency. Separation efficiency. Okay. For this case, first step, we utilize the mass balance. We utilize the mass balance equation. We use this equation. That's right. We use this equation. X over L y minus y0 for this case. If we call XL mean this case. XL is over L y minus y0. XL equal to S 6.5 divided by L 3 YL minus Y0. For this case, Y0 is the component in the heavy phase in the feed. Y0 for this case is the feed. The feed, Y0 for this case is the output of heavy phase. The output for this case is 47%. That's right, because we know 53% recovery. That means 50% of sitosterol move to methyl chloride. That means move to methyl chloride, and then remain 47% instead remain in the aqueous vegetable extract. That means the heavy fat is 47%. Okay, and then you can calculate XL as a function of YL. And then you calculate the extraction factor is KL divided by SK, we know 11.2. That's right. We know that you get 5. And then you substitute as over A. That's right. At the cross-sectional area like this. This equation is A, KA. This is the unknown we would like to calculate. You know E, you know Y0. That's right. You know XL is a function of YL and K. Substitute this. Okay. This is YL, and also YL. Okay. And thus you can calculate Ka is equal to 3 multiplied by 10 power minus 1 per second. That's right, per second. For this case, YL it can be cancelled because this divided by Y, divided by Y, divided by Y. You can cancel YL for that case, and then this only one unknown is Ka, and then you can solve for Ka. Okay, you know Ka, you can use this equation. Use this equation to calculate L, because for Ka is a constant. If you would like to recover is 90%, 40%, 30%, Ka also constant for this case. Okay, you use the information from the problem statement to determine Ka, and then you use Ka and other information to calculate the length that we would like to achieve 90% recovery. Okay, for 90% recovery, how about 0? This can do the same equation, but we did change. 90% recovery, that means only 10% remain in the heavy fat. 90% off, so you remove out and go to the light fat. That means it's only 10%. That means it remains the heavy fat 0.1 mile. You know this, and then you compare between L at 90% recovery, L at 50% recovery. That's right. You compare like this equation because this is S over A and E is the same. That's right. We only consider like this term. Or you can calculate directly. That's right. You can calculate directly by substitute Ka. That's right. And you substitute like this. You substitute S over A, Ka, E, and Y minus XL over K Y0. You can substitute directly, or you can compare like this term. That's right. You can compare like this term. And finally, you can solve for L is 3.26. 3.26. So you can do the ratio of this is equal to 3.26. And we know right, is the L for 53% is 0.6. And then you can calculate L for 90% recovery is 2. You can this for increase the length or increase the height of the column, also increase the percent recovery. Okay. Please remember that you can calculate L at this by substitute all the term for 90% recovery in this equation. You can do this equation. You know E, you know S, you know A, you know Ka from period. That's right. And then you can substitute YL minus XL over K divided by Y0. Like this. You know this, you can calculate by this also. Okay, I will stop the lecture for this about the different detection, and the next I will talk about the equate to fate.